Okay, so in our previous class, we were discussing about nested loop join, and then we were also analyzing the cost of the nested loop join in the worst case. And the worst case scenario is that we assume that we have memory available only to hold one block of each relation. We can hold in the memory one block of the inner relation and one block of the outer relation. The inner relation is S and the outer relation is R. And with that, in that case, we have analyzed and shown that these many block transfers NR into BS plus BN number of block transfers will be required, and NR plus BN number of head seeks will be required. Now let us consider the best case scenario. The best case scenario is that in which the one of the relations, and we put it as the inner relation, is too small that it can be accommodated only in few blocks, 2 or 3 blocks. And also we assume that we have enough memory available to hold the inner relation S entirely inside the main memory. So in this case, you have to read the inner relation S only once. You have to read the inner relation S only once. Now, so how many block transfers will be required? So certainly when you have to read this file, you set the head at the beginning of the file and read the consecutive blocks. So only BS number of block transfers will be required and one head seek will be required to read the file S. On the other hand, then you have to read the blocks of BR one by one, the blocks of relation R one by one, and the total BR number of blocks you have to read. So total BR plus BS number of block transfers will be required, and again, since you are reading the blocks, once you have read the file entirely as and kept it in memory, so you read the blocks consecutively from relation R, and that's why only one head seek will be sufficient. So total 2 seeks and BR plus BS number of block transfers will be required. So which is the optimal case? So as so what we can see that in nested loop join, if one of the relations is so small, sufficiently small that it can be accommodated entirely inside the main memory, then we can easily use the nested loop join with the minimum cost BR plus BS block transfers and 2 head seeks. However, suppose none of the relation is small enough that it can be accommodated in the main memory, and if we consider only the worst case scenario that only one block from each relation can be kept inside the main memory, then we have another algorithm called block nested loop join. In block nested loop join, what happens that, so again here also we have the assumption that we have enough memory available only to hold one block from R and one block from S. Now the difference is that if you see the algorithm, you see there are 4 nested loops. In the outermost 2 loops, what they're doing, they're picking one block from each of the relations. So you pick the first block of R and the first block of S in the available memory, and then what they are doing, they are comparing each tuple of the first relation with each tuple of the second relation in the blocks that has been brought into the main memory. That means now each tuples in the first block of this thing R and each tuples of the second relation S we compare. So we compare with the first tuple and then we compare with the second tuple with all the relations of the first block of the second relation. See, observe the difference with the previous algorithm, nested loop join and block nested loop join. In first case, what we were doing, we were taking the first tuple only of R and then we were comparing it with the entire relation S. Now we're not doing that in that sequence. We are taking the first relation here and then we are comparing only with the first block of S. Then we are taking the second tuple of R and then again we're comparing with the block and then third tuple until the end of the first block of the first relation. So that means in the first round, all the tuples of the first block of R and first block of S, their combinations will be tested. So in the second iteration, then this block will be replaced by B1 and then will be replaced by B2 up to the end of file S. So this is the algorithm. So now let us analyze the cost of this algorithm. So how many block transfers will be required to read S? So now we can observe what? So you pick the first block and then the second block up to suppose the nth block and then compare it with the first block of R. Now when this is done, you will replace it with the second block of R and then again you will start from B0 to Bn of the second block. That means this entire file is getting accessed how many times? BR number of times, where BR is the number of blocks available in R. So nested loop join, you read the file n number of times because in that case you compare with the first tuple the entire file and then the second tuple the entire file in that way. And how many head seeks will be required? Now in this case, what you are doing, you were reading this file first entirely consecutively. So since you are reading the file consecutively, only one seek will be required. One seek will be sufficient. And then how many times you were reading the file? You were reading the entire file BR number of times. So BR number of seeks will be required to read this file. How many seeks will be required to read this file? Again, to read this file, that depends on, the answer depends on, as I have discussed in the previous class, whether you are reading the blocks consecutively or that is being interleaved by some other operation. In this case, definitely it is being interleaved by other operation. After reading the first block, you were moving the head here, and then when again you have to read the first block, you have to move the head here, and then again you have to move the head here, because now you have to read this file again. So that means BR number of block transfers will be required to read this file also. So in total, BR plus BR, 2BR number of 6, not block transfer, 2BR number of 6 will be required. So in this case, block nested loop join, the worst case cost is BR into BR into BS plus BR block transfer plus 2 into BR 6. And if you remember how many 6 were required in case of the previous algorithm, that was NR plus BR, which is certainly much larger than 2BR, which is equal to BR plus BR, because number of records in the same relation is much larger than number of blocks. Now, what would be the cost in the best case in this algorithm? In this algorithm also, in the best case, and the best case means that the inner relation is so small that it can be kept entirely inside the main memory. So in this case, as in the previous case, the same thing, how many block transfers will be required, BR plus BS, because you need to read this file only once. So that requires, that demands BS number of block transfers. And then one by one, you read the block of these blocks of this file. So that will require BR number of block transfers. So this remains the same. The best case cost for both the algorithms, nested loop join and block nested loop join, remains the same. Not only that, the number of head 6 also will remain the same, which is 2 6, as you can analyze by yourself also. That only because you are reading the blocks consecutively for this file, so you need 1 seek here, and then again you are reading the files. After reading this file, you are reading the file one by one, the blocks consecutively. So one more seek will be required to read this file. So total 2 seeks will be required. So which is the, so in the best case, we can see that nested loop join and block nested loop join they have the same cost. But in the worst case, block nested loop join is definitely much cheaper than the nested loop join. Now the next algorithm is indexed nested loop join. Index nested loop join, from the name itself you can understand that it is applicable. You can apply this algorithm only when there exists an index. Now on which relation the index should exist? Actually, this indexed nested loop join is more suitable for a natural join. In a natural join between R and S, you know that there should be a common attribute, suppose A, and we check, we pick only the tuples with the common attribute values in both the relation, say R dot A is equal to R dot S dot A. So how can we perform this if we have an index on the inner relation S? Now what we can do, if we can pick each tuple of relation R, say T1, T2, in this way, T and R, if n number of tuples are there in the outer relation, we can pick each tuple, suppose T1, and then check the value of the attribute A in that tuple. Say this value is V. So what we do exactly now, the next step is that actually we apply sigma theta on S, where this condition theta is nothing but A is equal to V. We are checking for the condition, equality condition, A equal to V. So we have already studied the selection algorithms. There are 6 algorithms which you have already studied. Selection algorithms which take the advantage of an index, and then we can estimate the cost also of the selection operation depending on the algorithm that we choose. So in this case, what would be the total cost then? Let us assume that C is the cost of doing an index search on relation S, which we can easily calculate because we have seen the formulas that can be used to estimate the cost of algorithms. If you remember those algorithms, A2 to A7 for indexed base selection algorithms, we can estimate the cost of one selection. So what would be the total number of block transfers in 6 in this case? So what you have to do, you have to read the tuples T1, T2 up to TNR one by one. That means you have to read the relation R entirely one by one. So that means that will require BR number of block transfers. And how many 6 will be required to read this relation? That again repeating the same thing, the answer depends on whether you are reading the blocks consecutively or the operation is being interleaved by some other operation, secondary storage access related operation. The answer is that yes, it is being interleaved, because when you read the first block in the available memory B0, after that you have to do an index search, in memory index search. So you have to retrieve the index first from the secondary storage that is kept in some other location, and not only that, after doing the index search you will get a set of record pointers, and accordingly you have to fetch the corresponding records. So definitely the head is being transferred to some other location in between. So that means total BR number of 6 also will be required to read this one. BR number of block transfers and BR number of 6. Hence, total time consumed is BR into T plus TS, where TT is the time consumed for one block transfer and TS is the time consumed for one block seek operation. Plus, now after reading each of the tuple, you have to do, as I said, this selection, and the cost of the selection is C. So total cost is NR into C, because for each tuple you have to do this index search. So this is the total cost of indexed. Of course, this is the worst case scenario. This is the total cost of doing indexed nested loop join. Okay, and from this formula also we can understand that if indices are available for both of the relations R and S, from this formula we can understand that if BR and NR are reduced, then the cost will reduce. However, if BS and NS is reduced instead of BR and NR, then there is no impact on this formula. So that means we should use the relation with fewer tuples, the smaller relation, as the outer relation. Okay, so this is indexed nested loop join. Now there are other join algorithms also, like merge join, hash join, etc., which take the advantage of that external sort merge algorithm and hashing, but we'll not discuss these things in our syllabus. Just for the completeness of knowledge, we know that there exist some other algorithms also, like merge, join, and hash join. So basically, we have discussed three join algorithms: nested loop join, block nested loop join, and indexed nested loop join. You can study the algorithms along with their worst case, best case costs in terms of number of block transfers required and number of head 6 required to perform the operations. Worst case meaning only one block from each relation you can keep in memory. Best case meaning one of the relation is so small that you can entirely keep in memory. So we have discussed about selection operations, join operations, sorting operations, and these three operations we have discussed. Now let us have a look briefly on how the other operations can be implemented using those basic operations. Like for example, in order to do duplicate elimination is a very much demanding operation in database queries, specifically in projection operations and in many other operations also. You need to eliminate the duplicate tuples. So how can you do that thing? The simplest way is that you do a sorting. The algorithms to do sorting we have already learned. Now when you do sorting, then the duplicate tuples come consecutively. So they becomes adjacent. So it is very easy to detect them and remove all except one entry. But optimization can be done that when you are doing the sorting, as I said that in order to do the duplicate elimination, you can do sorting. But which algorithm are you using to do the sorting? If you use the external sort merge algorithm, then as you have learned, I have discussed that when you are doing the external sort merge, executing the algorithm, then at the intermediate level, some intermediate files, which we call the run files, R0 to Rn, number of run files are generated, which are also sorted files, but they keep only a portion of the data of the main relation, but they are still sorted. Now, since they are already sorted, so if you eliminate the duplicates from those sorted files, or rather, when you are creating the sorted files, you do not take the tuple if it is a duplicate of the previously entered tuple, then automatically the duplicates are not allowed in those run files, and when you merge those run files also, the ultimate output of the external sort merge algorithm, which is a sorted relation, contains no duplicate tuple. Another way is to take the advantage of hashing. If you are using hashing and you know that if the tuples are duplicate, then they will be mapped to the same bucket. And then also it is easy to identify the duplicate tuples and delete them. Next operation is projection. Now, projection, how can you perform projection? You first project the tuples and the column corresponding to the columns which has been asked, and then you can apply the duplicate elimination procedure as discussed above. Next operation is aggregation. Aggregation is some kind of group by operation, like the queries that you might have seen, that suppose select salary from employee. There can be some where condition also, group by age. So that means what kind of output we're expecting? Age, and this is okay. This is not salary. Some aggregate function, average salary or max salary or mean salary. So this will be average salary the data will be listed. So how to perform this operation, this aggregation? See, if you do a sorting first on this particular attribute, which you are using in the group by clause, on the basis of this attribute, if you sort the relation, then certainly the consecutive relation with the same value of age. So all tuples where the age value is 30 will come consecutively, and then you can apply an aggregate function on those tuples. It becomes easier, like duplicate elimination. If you sort the relation according to that clause, that attribute used in that group by clause, then the consecutive tuples comes with the same value in that attribute, and then you can easily apply the aggregate function. Another optimization what you can do, since the aggregate functions like average, maximum, minimum are associative, that means you can perform them in any order. So when you are doing the sorting itself, if you are using an external sort merge algorithm, then in the intermediate run files, you can generate the aggregate values like the aggregate salary, maximum salary, average salary, maximum salary, etc. You can calculate on the run files. And if you take the aggregate of those aggregated values, then also the result will be the same. So basically, these are the operations. Similarly, we can also implement union, intersection, and other operations. Okay. So this is the end of this chapter. So we have learned how to, let us have a brief review of the chapter, what we have learned. This is the basic mechanism we have learned that how SQL query is executed by the DBMS system. We have learned that it is translated into relational algebra expression, and then some optimization is applied, and optimization involves two things. And relational algebra may have multiple equivalent forms, equivalent expressions. We choose the expression with the smallest, lowest cost. Along with in an expression in the lowest cost, there are many algorithms. And each algorithm, like in order to implement each of the operation, selection, projection, join, we have several algorithms we have studied. So we choose the algorithm which will have the smallest, lowest cost according to the statistics of the data. And that is called an execution plan, where we have decided the final relational algebra expression along with the algorithms to be used for each of the operations, which is called an evaluation plan. And then evaluation plan is submitted to the evaluation engine, which takes the data and from the tables and then apply the algorithms as decided in the execution plan and finally generates the output. So that's all about the chapter. If you have any questions, you please mail me anytime. You mail me. I'll try to explain in the mail itself, or otherwise I'll give you time to meet me in my office. Thank you very much.